Hello there and welcome to this computer science video on the A-star algorithm. Before we jump straight into the algorithm and how it's made up and having a look at a few exam questions, you need to have some prior knowledge of Dijkstra's algorithm. And the reason for that is because the A-star algorithm is just like Dijkstra's. It uses the same setup, but it has a few extra steps, and that's because the A-star algorithm is a derivative of Dijkstra's algorithm, all right, or a version of it. The A-star pathfinding algorithm itself is used to find the shortest path from the starting point to a goal or its destination. And you might say, well, so does Dijkstra's. Well, yes, it does, but Dijkstra's looks at every node and every possibility from every node onto every other node, whereas the A-star algorithm uses the term heuristics to find the fastest path whilst ignoring some other nodes, therefore making it more efficient. You'll see it used in games, things like pathfinding for characters where enemies spawn and then move on to you, your character, or try and attack you, or things like GPS systems, traveling from A to B, for example, in the fastest possible route. Now, when you look at the A-star algorithm and break it down, it's just a mix of Dijkstra's, like I've already said, and something called a greedy best first search, which goes quickly towards a goal. So if you imagine drawing a line from A to B, and that line's the fastest route, or as the crow flies, as we say, so the most direct route without any obstacles, then we use that line to basically sway our algorithm to find or get to the destination. So the key idea here is that the A-star algorithm tries to find the shortest, most efficient path using the best cost and a guess. And that guess is called heuristics. And we're going to come on to that word a little bit later on and go a little bit deeper into it. So how does it work? Well, you're going to see a formula like this and you're thinking, whoa, John, whoa, too much, buddy. Simplify it. Slow down. Well, I will. However, you won't need that in an exam, I don't think, okay? But it's good to know the steps or the things needed to find the fastest cost. So let's start with the first one, Fn. N is just the node that you're at, and F is the total cost of the node itself. So with your knowledge of Dijkstra's, I'm just saying these words here, the cost of a node. So that's the amount, the number that's there, and that'll be with the heuristic value included, which we'll see visually a little bit later on. But we've got F, which is the total cost. That's what we're trying to work out. Then you've got Gn, and that is the actual cost to reach the node from the start. So if we start at node A and we're trying to get to node G, we've got to think about, well, A, B, C, D, E, whichever way we're going. We've got to add all that, or add all of them up to find out the actual cost. And then we've got the extra bit now for A-star, which moves away from Dijkstra's, and this is the heuristic. And that's an estimate of the cost to reach the goal from N. Confused? Slow down a little bit. Let's put it in a little bit of context. So imagine you're walking from your house, so that black circle is your house, and you're trying to get to the shop, okay? Now, I might say to you as a human, how on earth are you going to get there? And you just say, well, I just walk down here, I go along here, I might go along the top, pop in and go around there. That, to me, is the fastest route. Well, you're a human, so well done you. Okay, the computer can't work it like that. We might give the computer a grid and we might tell it, okay, this is my satellite navigation system. Here is my location. I want to get to there. We need to work out how to get there. So G is how far you've walked so far. So if I go, let's go here, for example. This is my location. And it might say, okay, well, you've walked along here and down here. So you've gone 3 squares here, and you've got another 2 squares to get to a third square there. Okay, that might be how far you've walked. That might be G. Then you've got H, a guess based on how far the bookshop, or I don't like saying books, the shop looks from where you are as the crow flies. So you might go, okay, I'll go as direct as I possibly can, gets me to the shop. And that has a cost. And that's our heuristic. But it's our most direct path. And then you've got F. F is your estimated total cost to get to the shop using this path. So if I try and stick to that path as much as possible, I might go down here, down here, down here, up there, etc. And I might get there. The idea is I'm trying to stick to this direct line as much as possible. And that's what A-star algorithms are trying to do. It's trying to stick to the most direct path and get swayed by that. So, if we take that knowledge and we expand it a little bit further, what the hell are heuristics? Well, it's a smart guess. So let's just pop some squares onto this little graph here. You see my little character starts off at, let's say, A, for example. Right, A. And they try and get to B. That's the worst B I've ever seen. Okay, there we go. Now, how on earth do we work out what the heuristic is? Now, the heuristic is the most direct route, isn't it? As much as possible. Now, you need to have that number. And how do you work it out? You might say, John, how am I supposed to work out a heuristic in an exam? Well, good news here, people, is it's given to you already. That's good, isn't it? Okay? But expanding our knowledge a little bit, we might use something called the Manhattan distance. So that is the Manhattan distance. That's because in New York, in Manhattan, all the streets are in rows and columns, and we can use the number of squares here to work out the number of columns we've moved across and the number of rows we've moved down. And that's the Manhattan distance. This one, from A to B, a diagonal, if we can move diagonally, is called the Euclidean distance. The Euclidean distance. It's named after some Greek mathematician a long time ago who came up with this stuff. So, a heuristic, it's just a smart guess. It gets given to you in the exam. You need to include it in your calculations, and in a grid, a common heuristic is the Manhattan distance, which if you can only move up, down, left or right, like characters in games can, or the Euclidean distance, if you can move diagonally. Now, the better the heuristic, the faster the A-star algorithm works, and the reason why we use it over Dijkstra's is because of this reason. If you're sat in your car trying to get to London, for example, there's so many different variables, the heuristics are actually pretty good because you've got all the different roads, you know, the speeds, you know, the bearing, the direction or compass, for example. That heuristic is pretty good. And your suggestions given to you by Google Maps or Apple Maps will basically be working towards staying on that line as much as possible to get you to your destination. Because there's no point in going to Scotland to divert across to the east coast, to go down south and then cut back into... That's just a stupid idea. So A-star keeps you on that line as much as possible. Okay? So what about the algorithm? What about the algorithm itself? Well, what are we trying to do? So there's an example of a graph. And I'm just going to read this algorithm out to you, and then we're going to apply it. So don't worry if you don't understand it at this stage, because we're going to apply it and it'll all make sense, I'm sure. So for each node, we need to look at them. Okay, and we're going to work our way to the heuristic. So we put the start node in an open list. Yes, a list. It's a data structure. Then we repeat until the goal is reached or no nodes are left. We pick the node with the lowest cost overall. Now we choose that from the open list. So we choose the node with the lowest cost, and then we move it to the closed list because we can't visit a node again once we've been there. Then we look at all of its neighbors. So we look around it, assess the costs, and for each neighbor, if it's not in the open list, we calculate the G, the F, and the H values and add it to the open list. So remember, that's the total cost of getting there. That's the cost of getting to the node. And then it's the heuristic value as well. So if it's already there, but you found a better path with a lower overall cost or a lower cost to get there, then we update it in our table. Once the goal is reached, we retrace the path from the goal to the start, and we found our fastest route. Okay, now let's apply this. Let's take that information and put it in an exam question structure. So you might need to reread that, but I'm going to go through those steps anyway and see what we can produce. Here's an exam question. A computer game has a building containing 7 rooms. There's a secret passage between each of the rooms, or there are secret passages between the rooms. Figure 3 shows the rooms and the passages between the rooms represented as a graph data structure. The number in bold below each node in figure 3 is the heuristic value because they're already provided. Perform an A-star algorithm on the graph shown in figure 3 to find the shortest path from A to G. A to G, people. That's where we're going. Show your working, the nodes visited, and the distance. So we've got to show our working, we've got to show the nodes visited, and we've got to show the distance we've travelled. You may use the table below to give your answer. There's the table. It's got a number of columns, and I think we can fill these columns out without any prior knowledge. We'll see how far we get. Then we've got the final path and the distance, and that's worth 7 marks. So are you ready? Okay, so we can fill out the first column, which is our nodes. We can put in here A, B, C, D, E, F, and we got G. Yes, we have G. We don't know what the distance travelled is because we've not actually run through the algorithm yet, but we do know the heuristic. So underneath each letter, there's a bold number, and I'm going to write that down in the heuristic. So A is 90, B is 80, we've got C is 43, we've got, where's D? D is 70, E is 20, F is 8, and G is 0, because that's our destination node. Okay, excellent. Right then. Now, distance travelled plus heuristic, previous node, we don't know this, we don't know. So where are we starting from? Well, the question says start from A, and we're going to G. So currently, I'm going to circle this because that's where I'm currently sat. I'm at A at the minute. Okay. Now, what nodes can A see? It can see it's connected to B and it's connected to C. So it's connected to B for a cost of 20. And the heuristic at B is 80. Okay. So what I'll do is I'll put in here the distance from A to B is 20. Its heuristic is 80. So distance plus heuristic, that's going to give me 100 in total. And what previous node? I came from A. So that's my previous node. Okay. Then I can also see C. So C's cost is 44. And 44 plus 43 is 87. And I came via the A node. Okay, wonderful. So I've done the first part of the algorithm. I've checked that I can get from B and C from A. And if we think about A itself, well, to get to A, it's no cost. That's 90 because it's 0 plus 90. Previous node is not applicable because we didn't travel from a previous node. Right, what do we do now then? What do we do now? Well, the next stage of the algorithm is we look to see what the distance travelled plus the heuristic is, and we're looking for the shortest number, and that is C. So now I've been to A. I'm just going to tick it off that I've been to it, and now I'm going to move. I'm going to jump to C. I'm not going to go to B because it has a higher cost, so I'm going to jump to C. Now C can only see one node. It can't go back to A because we've visited it, we've signed it off, get off, and we're now looking at E itself. Okay? What's the cost? So to get to E, it's going to cost us 22. Now, is that 22? Well, it's 22 plus the cost of 44, because that's how much it took me to get to C in the first place. So in actual fact, I'll put that in brackets. I'm going to run out of space here. I'm going to put in there 66. Okay, 22 to get to E, plus the cost of getting to C in the first place. And then that's 66 plus the heuristic is 60, 70, 86. 86 goes in. There we are. And it took me the cost of C. Oh, sorry, I came via C, didn't I? All right. So now I have to look in my table, sign C off. Look in my table. I've got 100 and I've got 86. Which one is lower? Well, this one's lower. Wonderful. So let's jump to E. There we are. Now, oh my goodness, look at all these things. E can see B, D, and F, okay? So let's have a look at B for a second. So what was my cost to get to E in the first place? Well, it was 66, okay? So it's 66 plus 56, and then the heuristic. Oh, what? What? So I know that 66 plus 56 is higher than the cost of getting to B originally. Okay? And then with the heuristic added, it's also bigger than 100. So this does not get replaced. There is a faster way to get there, and it's definitely not via E in the first place. Okay? Now, what about getting to D? Now, D has no value. In actual fact, these would be infinity in an actual algorithm, but we'll leave them blank. This here, E, has a cost of 66. Okay? So, 66 plus 62 is 128. 128. Then we add our cost of 70 on top of that, and that gets us 198. And how did we get there? We got there via the E node. At the moment, wonderful. And then I've got F down here. Now F hasn't been visited. So E's cost, again, was 66 plus the 15. 66 plus 15 is 81. Plus the 8 gets you 89. How did we get there? We got there via the E node. Now, I've done E, tick that off. So let's look at B. B's got a cost of 100. Let's look at D. D's got a cost of 198. And let's look at F. F has a cost of 89. So F has the lowest cost out of those three. Therefore, we jump to F. Okay? So F's cost of getting to F is 81. And I can only see one node, and that's G. So there's a cost of 9 to get to G. So 81 plus 9 is 90. There's no heuristic value, which means it's 90 overall, and we got there via the F node. Okay? And that means we got to G, so we would terminate the algorithm. Terminate the algorithm. Okay? You can look at the other node because there might be a faster path of getting there. And A star doesn't always, you might think it does, but it doesn't always find the fastest route. It's a best guess, is what it's trying to do. So in that case, if I'm at G, my final path was G. So let's go destination node. So there you go. G. How did we get to G in the first place? You look in the previous node and it says F. So I went from G. If I go backwards, it would take me to F. Look at F in the table. Where's F? F had a previous node of E. E goes in my table. Look at E's row. E went via C. Look at C in the table. C went via A. So the path I took was A to C to E to F to G. That was my calculated fastest route, and it took a distance of 90 to get there. Okay? Where do the marks come from then? Well, you get 1 mark, 2 marks, and that 2 marks is for those 2, because that was the first step after the first node. So 1 mark for those 2. Then you get 1 mark, 1 mark, 1 mark, and 1 mark, because they're all new nodes. 1, 2, 3, 4, 5, 6. And then finally, those 2, you get the 7th mark for those 2. Okay? And that's how we did it, people. That's how we did it. A couple of questions that I would ask is, what happens if the distance travelled and the heuristic are the same? What if they're the same? Then you apply the algorithm and choose one. It doesn't matter. You just choose one of them and continue the algorithm, because it's a best guess. We're trying to get to the end point. You just choose one and carry on. Let's see. Did we get these? Just checking that we're not going mental. Oh, that's good. Yep, perfect. A, C, E, F, G, A, C, E, F, G. A, C, E, F, G. Yeah, 90, 90. Wonderful. Okay. So in row A, you could have had NA, none, and null, or a blank cell. Many candidates demonstrated a good understanding of the A-star algorithm, and most candidates achieve at least some of the marks available, the most commonly given being the final path, often through inspection, and the first row of the table. A few candidates treated the algorithm as if it were Dijkstra's and explored all possible paths and routes rather than stopping as soon as the goal node was located. Oh dear. Okay. Right. So let's have a look at this next one. Some characters in a game will move and interact independently. Taylor is going to use graphs to explain the movements that each character can take within the game. Dancer Gold is one character. The graph shown in figure 1 shows the possible movements that Dancer Gold can make. There you go. Dancer Gold's starting state is represented by node A. Dancer Gold can take any of the paths to reach the end state represented by node G. The number on each path represents the number of seconds each movement takes. The number in bold below each node is the heuristic value from A. Define the term heuristic in relation to the A-star algorithm, and then perform an A-star algorithm on the graph shown in figure 1 to find the shortest path from the starting node to the end node, showing you're working, the nodes visited, and the distance. You may choose to use the table below to give your answer. This is 8 marks this time. So where do we start? Well, first we've got to consider defining the term heuristic. So it's worth 2 marks, and I said to you before that the heuristic is a smart guess, or an estimate, you could say. And it's an estimate that tries to guess the distance or the cost from each node to the destination node. So each node you land at, you're trying to work out the shortest path or distance to the destination node itself. And that creates a travel path for the algorithm to stick to and try to follow. And that speeds up the process of finding the solution. So what would I say for 2 marks? I would say a heuristic is an estimate or a guess that estimates the distance or the cost from each node to the destination node. That's it, 2 marks. Finished? Then what I would do is start to look at my algorithm table below, because that's where the bulk of the marks are coming from. And I'm going to put down my nodes. So I've got an A node again, B, C, D, E, F, and G. So A, B, C, D, E, F, and G. Okay, again, they've still got rows available, so they've done it to you again. And we can work out the heuristic, so the bold number in there, that's 90, 80, C is 65. We've got 50. F is 30 and G is our destination, so that's 0. Okay. Now we need to start moving our way through. We need to, where we're starting from, end state. So A to G is where we're going. So A, because we're there, distance travel is 0. The heuristic is 90, so it's 90 plus 0. Previous node, not applicable. There we are. Right, so what can A see here? So A can get to B for a cost of 21. And it can get to C for a cost of 42. We're both going via the A node, and then we add up what the heuristic will be. So 21 plus 80 is 101, and 42 plus 65 is 107. Okay, done that. Circle A, cross it out because we've been there, we can never go back again. Then we look at the distance and heuristic. Which one is lower? Well, B is lower, so then we move to B. B can get to E and D. So what was the cost of getting to B in the first place? 21. And what's the cost of getting to E? So if I put in here 21 plus 40 gets us 61. I'll just put that in there, 61. 61 plus 50 is 111. How did we get there? We got there via the B node. What about D? Well, D was, how much did it take to get to B? Forgot, 21. So 21 plus the cost of getting there now, which is 38. 21 plus 38 equals 59. 59, that's 109. And we got there via B. Okay, next node. Which one has the shortest cost that's not been visited? Well, suppose I have to tick off B because we've been there, so we can never go back again. Cross you out. Be gone. Look at the numbers. We've got 107, 109, and 111. The algorithm states whichever one's not been visited and has got the lowest number, 107. So I'm going to have to go back to C. So we jump to C this time. There we go. C. Right then. So now we're at C. We can only see D. So let's have a look. What was the cost of getting to C in the first place? So that would have been 42. Plus the cost of getting to D now, which is 12. And what does that make? That makes 54. Hey, wait a minute. 54 to get to D. You look at D's cost of 59 there, and you go, well, 54 is less than 59. So we have to basically remove, put a line through it, remove it, and we put a new cost of 54. So 54 plus 50 is no longer 109. It's 104. And we didn't go via B anymore. We now go via C. So we found a faster route, and therefore we update it. Wonderful. Great. Oh, well, that was interesting. Tick that off. C has been visited. Now, where do we go next? So our unvisited nodes, we've got D and E. Which one has the lowest cost? We're going to D, 104. So jump to 104. There we go. D can only see F. So what's the cost of D so far? Well, to get to D, it's going to cost us 54 plus the cost of getting to F in the first place, which is 23. And that gives us 50, 60, 70, 77. So getting to F is going to cost me 77 now. 77. Plus the heuristic cost of 30, and that is 107. 107. And I went there via D. So put D in the previous node column. There we are. Tick it off. You're done. You're done. Here we are. Which one's got lowest cost? 111 or 107? 107, please. Now I'm sitting at F. What was F's cost in the first place? It was 77 in total to get there, plus the cost of getting to G now, which is 33. So 77 plus 33 is 110 plus 0 cost, 110. We got there via the F node. Wonderful. I didn't go to E in the end, but I've ticked that off and I've arrived at G node. There we are. So what's my final path? Let's see. I've reached the destination. So that was G from destination. I look at the G row. I go along. Previous node was F, so I go to F. Go to F row. Previous node was D. And it was C before that. Previous node was C. Go to the C row. And it was A. A, C, D, F, G. For a total of 110. Okay. Wonderful. Each one of these rows this time gets you a mark. So it's 1, 2, 3, 4, 5, 6, 7. And your 8th mark comes from these two. And that's it. That is your total. So let's have a look. The first question, worth 2 marks. I said estimate. I'll take that, thank you. I said guess. I'll take that. I said this as well. Estimates the distance or cost from each node to the destination node. I didn't say this. I didn't say this. But I got 2 marks in that question, so well done to me. And what about this one? A, C, D, F, G. I got that, and I got 110. And they all look correct to me. You see how E doesn't have a tick because I didn't visit it? That's right. Perfect. Many candidates demonstrate a good understanding of A star. Most candidates achieve at least some marks. That was the same as the examiner comment from last time. A few candidates treat the algorithm... That's exactly the same as last time. No. Okay. There we are, people. So that is Dijkstra's algorithm. It's not, is it? That's A star algorithm. My goodness. It is like Dijkstra's algorithm, but you have to include the heuristic value, and at each step you assess the nodes that haven't been visited and have the lowest cost. You would then continue with them. If you find a lower cost, you update it in the table by putting a line through it and then continuing on with the algorithm. So I hope that helps. Let me know if you've got any questions. As always, thank you for watching.